Hello, welcome back to Algebra. The title of this lesson is Adding and Subtracting Radical Expressions. This is part one. We're going to have several parts where here in the beginning we'll be dealing mostly with problems with adding radicals that involve numbers and so on. And then as we go on, we'll get more complicated expressions, finally culminating in adding and subtracting these radical expressions that have variables like x's and y's. So the bottom line is we always learn how to add and subtract things after we learn how to multiply and divide them, because multiplication and division is actually easier to do. The reason is because when you add and subtract anything, if you have a fraction involved, then you have to deal with the common denominators and adding fractions, which makes it an extra step here. So what we're going to do is we'll present the problem, we'll simplify any radicals that we have, I'll explain to you when you can add radicals and when you can't. But ultimately, if you have any fractions, you're going to have to get common denominators in order to get to the final answer. So that's why we learn that after we've learned the multiplication and division, which we've already done. So let me get started here by telling you something that you already know, or at least reminding you of something that you already know. Forget about radicals for a second. Let's talk about just basic algebra for a minute. Would you agree that you already know how to add 2x plus 3x? Well, we already talked about a long time ago the concept of like terms. This is 2 x's, this is 3 x's. X can be a number, it is a number, we don't know what it is, but the idea is that this x exactly matches this x. So when you add things in algebra, in general, you can only really add them if you have the same variables. And that's because it's kind of like you're adding 3 buckets of potatoes to 5 more buckets of potatoes. So you add those together and you get however many total buckets of potatoes, right? X might be the number of buckets of potatoes, for instance, right? But if you have 3 cars, like automobiles, and 3 jumbo jets, I mean, you could add them, I guess, but you're not going to get anything useful. I mean, what does it mean to add those things together? So we have like terms because we have to be adding the same thing together. And you all know from basic algebra that this is 5x. But you would also agree that you learned a long time ago in basic algebra, for instance, that if you try to add something like 2x plus y, what does that equal to? Well, there's nothing to do, right? Because you have 2 x's and 2 y's. So this would be like adding 2 automobiles to 1 jumbo jet. I mean, you could add them, but you really can only have a meaningful answer if they represent the same thing. So really, if you're going to simplify this, you really can't do anything. It's just going to continue to be 2x plus y, and you're just kind of stuck with it. You can't really add it anymore. Now, the reason I'm bringing that up is because it makes the understanding the following a lot easier. What if I tell you instead of x's and y's, so forget about x's and y's for right now, what if I ask you to add the following things? Square root of 2 plus the square root of 3. How do we add that together? Well, the square root of 2 is a number, right, whatever it is, and the square root of 3 is also a number. So the first thing you try to do is you do a factor tree, but 2 can only be written as 2 times 1, and 3 can only be written as 3 times 1. So you really can't simplify those radicals at all. That's the first thing you try. So you're stuck with really trying to add square root of 2 and to square root of 3. So the idea here is when we're adding and subtracting radicals or any expressions involving radicals, just like the case with variables, you can only add or subtract them if you have the same radicals, right? So this is, of course, a square root, and this is a square root, so that's the same. But here you have the square root of 2 and the square root of 3. And no matter how much you want to, you cannot add those together. You can kind of think of them almost like variables where you can only add them if they're like terms. The idea is the square root of 2 and the square root of 3. Yeah, they're both square roots, but they're really not like terms. Just like x and y really are not like terms. So the idea is if you really want to add this together, you can't really do any more, so you just say it's not possible, right? To simplify that further, you could just circle this as the final answer because there's nothing else to really do. Just like in the case of this, there was nothing else to do. It would just say, well, this is as simple as I can get. Now let me compare and contrast that to the following problem. Let me change the problem slightly. I still have the square root of 2, but I'm going to add to that 2 times the square root of 2. So what do I have here? You can think of the square root of 2 as an object. It's like a thing, right? Like, I know it's for the square root of 2, but you can kind of think of it as like apples, okay? So here I have two of these things, we call them apples or whatever, but it's something, it's the square root of 2. And here I have another one of these things called an apple. There's an invisible 1 in front of here. So here I have one of these things, and here I have two of these things. So I can add those together to make three of those things. Three of what? Well, three of these things that we're calling square root of 2. So really you have one quantity of the thing called the square root of 2. You add it to two more things that we call the square root of 2. And I can add them together only because they're like terms, because these are exactly the same, just in the case, exactly as the case of variables above. So this is the final answer. So that is pretty much the extent of what most books are going to teach you, is that you can only add these radical expressions. You can only actually add them together if they exactly match. If the radical itself, it has to be a square root and a square root, or a cube root added to a cube root, or a fourth root added to a fourth root, or whatever. That has to match. Also, what is underneath the radical has to exactly match. All numbers and so on and so forth have to also match in order to be able to add them. Then when you add them, you just add the coefficients, which are sitting out in the front. All right, so now that we have the very, very basic preliminaries out of the way, we're just going to work a bunch of problems, slowly building up complexity so that you can see how to handle that in different cases. What if I have 3 times the square root of 3 plus 6 times the square root of 3? And I want to ask you, how do you add those? The first thing you do is you say, well, square root of 3, square root of 3. Can I simplify them? Well, I really can't. Square root of 3 is not going to get any simpler than that. This is a like term match with this, so just like in algebra, we add the coefficients. 3 plus 6 is 9. 9 what? 9 times the square root of 3, because I have a quantity of 9 of these things, because they're objects kind of, and I'm adding those together. Now here is where almost everyone I think can actually understand this. And if the problems just stayed to that level of complexity, life would be very easy. But quickly you run into problems like this. What if you have the square root of 50 plus the square root of 18? So then you would look at this and you're going to do exactly what I'm telling you, that you can only add them if the radicals are the same and what's under the radical is the same. And a lot of students will say, well, I don't know what to do because you said I can't add them because they are different, right? That's true. However, I told you the first thing you should do is always try to simplify the radicals. Obviously, I cannot add them because they're as is, because they are different. But just like fractions, you have to, in order to do a fraction addition, you have to get a common denominator before you do anything. If you're going to subtract fractions, you got to get a common denominator. If you're going to add variables, you have to have common variables. Here, these look very different, but what we're going to do is move over here and see if we can simplify this. So we're going to look at the square root of 50 first. So 50, doing our factor tree, is 2 times 25, and 25 is 5 times 5. Now this is a square root, right? So we're looking for pairs of numbers, and we see a pair of 5s. All right, so we're going to hold that in our back pocket for a second. Let's go over here to 18 and see what we get. 18, you can write however you want, 6 times 3 or whatever. I usually do 2 times 9 is 18, and I know that 9 is 3 times 3. So I have prime numbers all in the bottom there. And you're looking for square roots, so you're looking for pairs, right? So now I know how to write those. So what I have then is the square root of 50 is written as this single 5 will then come out, because it's a pair, it comes out. But underneath the radical remains the 2, because it's an orphan, there's no pair for him. And then you'll add to that the square root of 18, which you're looking for a pair. It only comes out as a quantity of 1, so the 3 only counts one time. Underneath the radical is a 2, which is what is left over. Now look what you have. If I cover this up and I just give you this problem, you know how to handle that because the square root of 2 matches the square root of 2. We just now add the coefficients. How many of them do you have? You have 8 of them. 8 of what? Well, 8 of these things that we're calling a square root of 2, which is just a number. So we'll just circle that. Now I'm going to say here from the beginning, if you have no idea what I'm doing here with the factor trees, if you have no idea that we're looking for pairs of numbers in these factor trees and pulling out of the square root, if you just lost already, then it means that you have not watched my lessons on basic simplification of square roots and cube roots and radicals. So at this point you would need to stop, you would need to go back to my lessons on that because that's an even more basic skill. Algebra is like building a house. There is no way you're going to do these problems in this lesson without a good foundation in radicals. So you have to know how to simplify them, and this little tree thing is the way we do that. It's called a factor tree. So go back to the previous lessons and master that, and then come back and meet me here. But the idea is we try to simplify these radicals, and then we see what we get. And if we have a matching like terms, then we can add them as usual. All right, so with those preliminaries out of the way, now we know how to proceed for every problem that follows. What if you have 3 times the square root of 12 minus the square root of 48? So obviously we cannot subtract them. I know you might think 12 times 4 is 48. Maybe you can do something like that, but really you can't. You can't make generalizations like that. So really we're going to try to simplify the square root of 12. So we go over here and write a 12 and we do a factor tree. We know that 3 times 4 is 12. We know that 4 is 2 times 2. All right, so we're done with that factor tree. We're looking for pairs because it's a square root. If these were cubed roots, we'd have to be looking for triplets. But we're not. We're looking for pairs. Then we have the square root of 48. So what do you do for 48? You can pick what you want, but usually I go with 8 times 6 is 48. And I know that 8 is 2 times 4. And I know that 4 is 2 times 2. And then I know that 6 is, let's see here, 2 times 3. I'll try to write it a little bit intelligently so I can circle it properly. So now I'm looking for pairs. So I see I have a pair of 2's here in the bottom of the factor tree, and I have a pair of 2's here, which is also in the bottom. This 4 is not in the bottom of the factor tree because notice we split the 4 off, so the 4 doesn't participate, but the 3 is orphaned. He's left alone. There's no pair for him. And so then we go over here and just write what we have. 3 times the square root of 12. You still have the 3 out front, but the square root of 12 means that we have a 2 that comes out, a single 2, square root of what is left over, which is 3, minus the square root of 48. We have a single 2 that comes out, but then we have another 2 that comes out, and the square root that's left behind is what is left over, which is a 3. So each of these counts one time, multiplied. Here then we have 6 times the square root of 3 minus, this is 4 times the square root of 3. Now look at what you have. You know how to solve that because we've done it about 4 times already. We have a common term, but it's subtracted. So 6 minus 4 is 2. 2 what? 2 of the quantity of what we call square root of 3. That is the final answer. 2 times the square root of 3. Pretty much every problem that follows will basically follow the same idea. Even when we get down to variables, when we have square root of x times y and we're trying to subtract it, square root of y times z or something, it'll be the same kind of thing. You can only add or subtract them when the radicals match, and when what is underneath those radicals are identical, then you add and subtract the coefficients. But as the problems get a little more complex, we'll have fractions involved that you have to deal with. We'll have exponents involved, but we're building your skills as we go, so you'll get good as we go along here. What if you have 5 times the square root of 2 minus 2 times the square root of 5? Now I know it looks irresistible to do something with this because 5 root 2, 2 root 5, it looks like they're mirror images of one another. But basically it's not possible to simplify this any further, not possible. So if I had to circle something, I would either circle not possible or I would just say this is actually already simplified. Why? Because I have a square root of 2 here and I have a square root of 5. So I can't actually subtract the coefficients because this is not a like term from this. This would be exactly like the case over here where I have 2 x's and 1 y, and I can't really add them because x and y is different. So this is a different term than this one. It's a different object, so to speak. So I can't do anything with it. Now, of course, you should try to simplify it, but 2 can only be written as 1 times 2. So there's no pairs. I can't simplify it. And 5 can only be written as 1 times 5. So if you do a factor tree for that one, it won't be any simpler either. So because you can't simplify it, you have no options. It's just already as simple as it can get, and that's just it. All right. We have a few more in this lesson anyway, then we'll have more in the following lessons. Let's increase the complexity a little bit. Let's do 3 of these things. What if we have the square root of 6 plus the square root of 36 plus the square root of 216? So we have 3 radicals that we would like to add together. And it's the same rule though. The only way you can add them is if the radicals match exactly. Now these are all completely different. So the first thing you try to do is simplify them. So we'll go over here to 6. We'll simplify the square root of 6. Well, that's 2 times 3. Unfortunately, these are already prime numbers. There's no pairs, so the square root of 6 is not going to get any simpler than that. Well, then you look at 36, and I know you all know the square root of this, but if you've forgotten, 36 can be written as 6 times 6, which is a pair, so we know that the square root of 36 is 6. So this is going to resolve down to a number. And then the final thing we'll do before we finish it up is we'll take a look at 216, and we'll try to do that. So you might need a calculator for this. You know it's an even number because it ends in 6, so just divide it by 2. And you do it by hand or do it with a calculator, and you'll find out that 2 times 108 is equal to 216. This is also even, so divide it by 2 again, and you'll find out that 2 times 54 is 108. Now we're finally into smaller numbers, so I know from multiplication that 9 times 6 is 54. I know that 6 is 2 times 3, and I know that 9 is 3 times 3. So I have all prime numbers in the bottom of my tree, and I start looking for pairs. All right, so I have a pair right here, 3 times 3, and I have a pair right here, 2 times 2. The only thing left in the bottom is the 2 times 3, and there's no pair for that. There are no pairs for that, so I've done as much as I can. So then I come back over here and I say the square root of 6 could not be simplified any further, so I leave it exactly as it is, square root of 6. The square root of 36 came out to a single 6. You should know that already because 6 times 6 is 36. And then the 216, the root of that, comes out to a single 2 that comes out, a single 3 that comes out multiplied with it, and then underneath is everything that's left, which is also multiplied together, 2 times 3. So I'm writing this 2 times 3. So the next line is going to be square root of 6 plus 2 times 3 is 6, square root of 6. Now you can see what's going to happen. I cannot add this to this, and I cannot add this to this. However, these are like terms. Square root of 6 matches. I have an invisible implied 1 here, so 1 plus 6 is 7. And then, of course, I have this whole number. So I'll write the whole number first, and then it will be 7 times the square root of 6, because 6 plus 1 is 7. And that's the final answer. As much as you want to, you cannot add these together. Sometimes students will say, well, here's a 6 and here's a 6. I'll try to add them somehow. It doesn't work that way. The only way you can add them with radicals involved is if you have an exact match for a radical, and then the other term has an exact match for the radical. Everything's identical. Even though you have a 6 here and a 6 here, there's no radical here at all. So you cannot add these together as much as you want to. You just can't. Right? So that's the final answer there. And we're just going to increase the complexity a little bit. Actually, the next problem is pretty much similar level of complexity, I would say, but it gives you good practice. What if you have square root of 50? And you're going to add to that the square root of 63. And then you'll subtract, we'll finally do some subtraction here, 32. But the subtraction, the same rule applies for addition. Everything's the same. The only way you can subtract any of these is if the radicals exactly match. Obviously, these are all different. So there's no way you can add them as is. So we go over here and see if we can simplify them. 50 goes to 2 times 25, and 25 goes 5 times 5. Here is a pair of numbers. So I know I can write that like that. 63 goes as 7 times 9 is 63, and 9 goes to 3 times 3. Now this is an orphan, there's no pair, but the 3 times 3 definitely does have a pair. And then I have 32. There's many ways to find factors of 32. You can do 8 times 4. There's other ones you can do. I'm going to do 8 times 4 because that's what I remember from my multiplication tables. 4 can be written as 2 times 2. 8 can be written as 4 times 2, like this. 4 times 2 is 8. And then this 4 is 2 times 2. And then I'm going to look for pairs. And I see a single pair here and a single pair over here. I still have a 2 that is unpaired. This 4 doesn't participate at all because it's already broken down. So the bottom of the tree is here. So what you get is, when you put it all together, the square root of 50 comes and simplifies as a single 5 that comes out, square root of what is left over, which is a 2. The square root of 63 is written as a single 3 that comes out, with a square root of what is left over, which is 7. And then the 32 is written as I have a pair of 2's that comes out, one from this pair, one from the other pair, and the only thing left is a square root of 2. Square root of 2. So you can see right now you're going to have a match here. But just to be clear, we'll have 5 square root of 2 plus 3 square root of 7, whoops, not 6, 7, minus 4 times the square root of 2. So you have a match here, a square root of 2 and a square root of 2, it's a like term. So you look at the coefficients, 5 minus 4 is 1 times the square root of 2. So that's going to be written as just the square root of 2, has an implied 1 out here, plus 3 root 7. This is the final answer, square root of 2 plus 3 root 7. As much as I want to, I cannot add these because they have totally different radicals. Yes, the square root matches, but what's underneath does not, so I can't do anything with that. All right, so far we have done with or dealt with square roots. And obviously square roots are important because they're the most common radical that you're going to run into. But the same rules, exactly the same rules, apply if you have cubed roots or fourth roots or whatever. So the next problem will involve a cube root, and then the problem after that will involve a little more complicated problem when you have fractions involved with radicals. So the next problem is, what if I have 54, but I'll take the cube root of it, so I write a 3 right there, and I'll add to that the cube root of 40. Whoops, I have to put a 3 here to indicate that it's a cube root. And then I'll add to that the cube root of 16. Oops, not the cube root of 16. No, that would be the 16th root. So I'm going to put the cube up there, cube root of 16, like this. So I know it's getting a little boring, but what you do is you go off to the side. I recommend not destroying what you already wrote down. I recommend going to the side so you can kind of keep this separate. So what we'll do next is we'll move over to the side and we'll try to find out and simplify what these cube roots are. So we have 54, and we'll go a little faster because we've done this a few times. We know that 9 times 6 is 54. 6 is 2 times 3. And actually, let me write this. You'll see why I'm going to write it like this in a second. But the 6, let me write it as 3 times 2, right? Instead of 2 times 3. And then the 9 is 3 times 3. So now you are looking for triplets of numbers because it's a cube root. And now you can see I wrote it as 3 times 2 so I could more easily circle the 3. If I flipped it backwards, I'd have to circle them and kind of separate them. So that's the grouping that will be there. Let's go and do all the factor trees first, and then we'll simplify our problem. We know that for 40, we know that 8 times 5 is 40. You could do 4 times 10 if you want. It's going to give you the same thing. The 8 is going to be 2 times 4, and the 4 is going to be 2 times 2. There's nothing left to do with the 5. And so then I'm looking for triplets because it's a cube root, so I'm going to circle those. And then the last one we have is 16. Let's see what that's equal to. 16 is 4 times 4, which is 2 times 2, and then 2 times 2. And again, I'm looking for triplets because it's a cube root, not a square root, so I'm going to circle all 3 of those. So now I have everything in place to simplify this. The cube root of 54, this 3 only counts 1 time because it's a cube root, so it comes out, and then what's left under the cube root is just the 2 that's left over. Then for the cube root of 40, these 2's only come out 1 time. And what you're left with is what is left over. This 4 is not part of it. It's already been taken care of. We have a 5 left over. And then the cube root of 16, we have a single 2 that comes out times the cube root of what is left over, which is 2. So that's a simplification. Now you see what to do. You have a cube root of 2 and a cube root of 3. You can add those. Of course, you can't add it to this one because it's different, but you can add it to this. So the coefficients here is 2 plus 3, which is 5. So you're going to get 5 times the cube root of 2 plus 2 times the cube root of 5. Let me double check myself. 5 cube root of 2 plus 2 cube root of 5. That's the right answer. 5 cube root of 2 plus 2 cube root of 5. I always want to make sure I don't screw something up. Also, don't get confused. This is not 5 cubed. This is not 2 cubed. This is 5 times the cube root of 2. This is 2 times the cube root of 5. It gets a little confusing when you have these 3's out in front of the radicals, but you got to keep that straight or you'll get confused. All right, so far we've had addition and subtraction, square roots, cube roots. It follows the same cookie cutter recipe every time. You have to get good at the factor trees and so on. But here's a problem that's going to require us to use some other properties of radicals that we've already learned in the past. What if you have 27 fifths? So that's a fraction. I'm going to take the square root of that. And then I'm going to subtract from that 3 fifths. But, of course, I'm going to have a radical around that. So how do I do that? So first of all, you can only add or subtract radicals if the radicals match and also what is underneath matches. Obviously, 27 fifths doesn't look anything like 3 fifths. Now, some students will start doing crazy things like they see a common denominator here, and they'll start putting it under a common radical and then subtracting 27 minus 3 over 5. But what you're doing when you do things like that is you're making up math, because I never taught you that you can combine radicals like that. I said the only way you can add them is if they completely match, right? We never said anything about combining under a radical. Now, if they were multiplied or divided, you can combine under radicals with multiplication, but these are not multiplied, these are subtracted. So you have to look at if you don't know exactly what to do, you have to look at what do I know? What am I comfortable with? What do I actually know is actually factually correct that I can do? Well, I do know that if all I was given was this radical, it was a radical of 27/5, I can break that radical up as 27 square root over 5 square root. We learned that before. When you have a radical of a fraction, you can break it up like this. See if I can make this a little clearer, like this. And then if I just gave you the 3/5, I could do the same thing. So it would be radical of 3 and then square root of 5. And of course, these two things are subtracted. So I'm just breaking it up literally because I know that the radical of a fraction can be written like this. That's a property we learned before. If that doesn't look familiar to you, you need to go back and look at some of the previous lessons. And then we look at it and say, okay, so now we have two fractions. Yes, the fractions are ugly. Yes, of course. But I do have a common denominator. So here's where you have to start using your math, right, that you know that from previous math. If this were, instead of square root of 27 and all that stuff, and then the square root of 5, if it was like 2/5 minus 1/5, you know how to do that, right? Because all you're looking for is that you have a common denominator. It means the same number here. So you'd keep that common denominator, and then 2 minus 1 would go on the top. So it would be 2 minus 1, which you know is 1. So it would be 1/5, like this, 1/5, like that. You know how to do that. But here it looks a little bit different and a little bit harder, but you still have to look at the big picture. It's a fraction minus another fraction. The fractions have the same common denominator. It's just a radical on the bottom. I know you don't like radicals on the bottom, and we don't like radicals on the bottom, but it's just a number, and this is the same number. So whatever this fraction subtracts to be, it has a common denominator, square root of 5, just like we kept the 5 over here. So then how do we subtract the numerator? Well, just like we did it here, we kept the denominator, we said 2 minus 1. Well, this one is a number minus a number, right? We subtract the numerators like usual, so 27 minus 3. Now I can write it like this because I know that I can't actually do the subtraction right now, but whatever it ends up being, it's still going to be 27 minus 3, the subtraction of the numerators, over the common denominator. Now this looks even more complicated, depending on your opinion, but even more complicated than the original thing. So at this point, you need to start thinking about simplifying these radicals. I can't simplify the 5. I cannot simplify the radical of 3 because those numbers are too small. If I do a factor tree, I'm not going to simplify it. But 27 can be written as 9 times 3, and 9 can be written as 3 times 3, right? So I'm looking for pairs because it's a square root, and I have a pair of 3's right here. So this square root of 27 in the numerator can be written as a single 3, which gets pulled out, and a single 3 which remains underneath, which is from here. Then I'm going to subtract the square root of 3 that I have there, and then on the bottom I'm going to have the square root of 5, which I don't like that on the bottom. I'll deal with that later. Now the top I can subtract now because I have the same radicals. 3 minus the implied 1 here is going to give me 2 times the square root of 3 on the top, and on the bottom I have the square root of 5. So we've done the actual subtraction. We have a fraction minus a fraction, and we figured out after we've done the subtraction that the top is 2 times the square root of 3. The bottom is a number. It's just the square root of 5. We don't like square roots on the bottom, so we're going to get rid of it. How do we get rid of it? Well, let's write it over here. We're going to say that this is 2 times the square root of 3 over square root of 5, and we're going to multiply by the square root of 5. We've done this many times in the past, over square root of 5. When you have a square root, you can just multiply by the bottom. What's going to happen on the top, right? Well, let's do what's going to happen on the bottom first, actually. On the bottom, when we have two radicals multiplied, we multiply the inside of the radicals, which can be written as 5 squared, but that we're going to have the square root of that, so you can see the square root's going to cancel with the square, so we're going to get a number back. And on the top, what we're going to have is we're going to have the 2 all right, and we're going to multiply these radicals. Remember, we learned from multiplying radicals before that you just multiply the insides. 3 times 5 is 15. And it goes under a common radical. So if you're not familiar with this, when you multiply radicals, what you do is you multiply what's under them and wrap them in a common radical. If that doesn't look familiar to you, then you need to go back and learn how to multiply radicals, which we've already done. All right? So you have 2 times the square root of 15 on the top. 2 times the square root of 15 on the top. On the bottom, you have the square root of 5 squared. So you can think of the square root canceling with the square, leaving just the number 5. This is the final answer. Now you can try to simplify this square root of 15. You can go and do a factor tree, but 15 can be written as 3 times 5. 3 is prime, 5 is prime, so there's no other parts of the tree, so there's no pairs. So the square root of 15 cannot be simplified anymore. We have a number out in front and a number on the bottom, and the number on the bottom is not a radical anymore. This process of multiplying, making it a square underneath and canceling it, basically means that you always get a number left over. So we don't have a radical in the bottom anymore. So this is a good lesson in adding and subtracting expressions that have radicals in them. The only way you can add or subtract them is if they have like terms, where the term is the radical has to exactly match. It's the only way it's going to work. You can't add or subtract unless that happens. So all of these problems involve simplifying the radicals, seeing if you have common terms, and adding them. If you have wrinkles in here, like fractions, then you'll have to use other things that we've already learned, like how to break these things up. And then you see you already have a common denominator here. So you subtract the numerators as usual. Then you simplify the radical 27. Then you see you have a common term, subtract them, and then you just go through it from there. Every problem will be different. There's never going to be the exact same path you get through for all of these problems. They'll all be different. So follow me on to the next lesson after you have solved these yourself. And let's get some practice solving some more complicated expressions, simplifying expressions that involve radical addition and subtraction.